So next speaker is Svetlana Klepikova. She will talk about the spectrum of the curvature operators in four-dimensional network groups.
Okay, I want to tell about history of this talk. The problem of establishing connections between the curvature topology of Riemannian manifolds is one of important problem in the Riemannian geometry. There are many scientists around the world involved of solution this problem. For example, John Milner investigate the curvature of three-dimensional metrically groups, the problem of restoring of locally homogeneous Riemannian manifolds by prescribed values of spectrum of curvature operator was solved by Aldrich Kowalski and Stano Nikshevich. The similarly result was obtained by Dmitry Skorbin, Olesya Khromova, and Evgeny Rodionov. Kremlov and Nikanorov investigate the signature of Ricci operator on four-dimensional Lie group with left invariant Riemannian metric. The aim of this work is to investigate the signature of a one-dimensional curvature operator and the sectional curvature operator in the case of four-dimensional metrically groups. Let we have n-dimensional Lie group with correspondingly algebra and left invariant Riemannian metric. And nebula is the Levi-Civita connection when formulas for calculating the Riemann tensor, the Ricci operator, and one-dimensional curvature operator are presented on the slide. Riemannian metric induce the scalar product in the bundle for the rule. For this rule. When the Riemann tensor at any point of manifold can be considered by the sectional curvature operator, which formula is presented on the slide. In this slide, the mathematical model with using the components of the one-dimensional curvature operator is calculated as structure constants and metric tensor. Here, gamma E, J, K is the Christoffel samples of the first type. Gamma I, J, S is the Christoffel samples of the second type. S is a scalar curvature. And for the mathematical model for calculating the components of the sectional curvature operator can be built similarly. The studying the properties of the curvature operator is interesting for understanding the geometrical and topological structure of Riemannian manifolds. Therefore, it is natural to try to find the general properties of each operator. One of the variants is to investigate the signature of the spectrum of the curvature operator. What's a signature? As a signature of the symmetric operator B, we mean an ordered set of signs of eigenvalues curvature operator. Also, in the slides, the table in which all possible variants of signature of curvature operator in the case of four-dimensional metric Lie groups are presented. Also, we use Muratyanov classification of metric Lie algebra. There are 24 metric Lie algebra. Now I will formulate a part of result of investigate of one-dimensional curvature operator. For example, one-dimensional curvature operator on metric Lie algebra of this type, where A is the structure constant, can have only next signature. Let's prove this theorem. In the slide, the eigenvalues of one-dimensional curvature operator are presented. We can see that for all values a and b, eigenvalue a1 is less than 0 and eigenvalue a3 is more than 0 always. And consider the product of eigenvalues a3 and a4. We can see that also for any values of a and b, this product is always less than 0. From this follows that eigenvalue a4 is less than 0 always. And in the slide I presented the initial signature which realized by these values of a and b. And theorem is proved. Now let one-dimensional curvature operator on metrically algebra of this type can have only next signature. Let's prove in this theorem. The characteristical polynomial for the one-dimensional curvature operator in this metrically algebra is presented on the slide. Also in the slide I presented the table in which we show the initial signature and values of a, b, and c for which the signature is realized. And also we see that for all values of b, eigenvalue a1 is less than 0 always. From this follows that only the signature which presented in the slide are not realized. Also, using the Vieta formulas, we see that for any values of b, the sum of eigenvalues a2, a3, and a4 is more than 0, and the sum of the product of eigenvalues is less than 0. From this follows that only the initial signature can realize. No more variance. The theorem is proved. Now I will formulate a part of result of investigation of signature with sectional curvature operator in the case of four-dimensional metrically algebras. The sectional curvature K on the metrically algebra of this type can have only following signature. Let's prove this. In the slide are presented the eigenvalues of the sectional curvature operator in this metrically algebra. What can we see? If b is equal to 0, when eigenvalue k1 is less than 0, and other eigenvalues is equal to 0. From this follows that only this signature is realized. If b is not equal to 0, we can see that eigenvalue k1 is less than 0, eigenvalue k2 is 2 less than 0, eigenvalues k3 and k4 is more than 0, and eigenvalues k5 and k6 is equal to 0. From this follows that this signature is realized. The theorem is proved. And now the section curvature operator on metrically algebra of this type can have only this signature. Also we prove it. In the slide are presented eigenvalues of the sectional curvature operator in this metrically algebra. What we see is if b is equal to 0, when only this signature is realized. No, if we see on eigenvalues, we prove it. Consider the product of eigenvalues k5 and k6. We obtained that this product, if b is not equal to 0, this product is less than 0. from this follows that only this signature is realized in this case, and theorem is proved. In conclusion, I want to say that the similar theorem can be built for all 24 types of metrically algebra and this theorem can be extended for the case of locally homogeneous Riemannian manifolds. That's all. Thank you for attention.
Is there any question?
So I don't understand something. As I understand, Ricci operator acts on, this is symmetric to form. It depends on two vectors.
Yes.
It's correct?
Yes.
So how many, and the same curvature operator, yes? It's symmetric to form.
Yes. Yes, it's true.
So, but you show 4 eigenvalue, or how many eigenvalues for in dimension 4? It's
For the sectional curvature operator?
I understand for curvature, but how many was eigenvalues for curvature operator?
For the one-dimensional curvature, eigenvalues is
How many?
for eigenvalues for
Four? I
one-dimensional.
don't understand. Why 4?
For
It's on pairs of vectors, not on vector. So for 4 dimensions, how many symmetric vectors? So
The curvature operator, it acts on bivectors, so it's on 4 vectors. So there are 6 eigenvalues.
Section curvature.
So you
Sectional
Out of
curvature
something
operator
like 6.
is built on
It's
big
4.
vectors.
This operates.
It's wedge project, it's wedge square. X on the wedge square of
Acts on pairs of wedge square.
spectrum of the curvature.
And this technique can be generalized on locally homogeneous manifolds of what dimension? Of only of 4 dimensions? Yeah. Or maybe this can be generalized for some kind of many dimensional spaces.
I don't have answer on this question.
Can I? Technique is for any dimension, but we don't have a classification. Yes. For 4 dimension, we have classification, Lie groups and locally homogeneous, but for 1 dimension, don't have.
And are there some maybe series in 5 or 6 dimensional groups of some
we have,
series?
Montbarziano's classification for 5-dimensional Lie algebras, but not locally homogeneous. And for 6-dimensional solvable Lie algebras, if I'm right.
And maybe if not the classification, complete classification, but some restrictions, so you can say that this signature is not allowed. There could be some rules that say
It's
that
very
not all signatures are allowed. For certain dimension, it may depend on also on dimension.
Very interesting.
Some general facts, because it's absolutely hopeless to try to extend classification to higher dimension, and maybe not reasonable because it becomes not treatable.
Yes.
But to try to find some general rules like that
But
would be
for
interesting.
example, 3 and 4, we can make some conjectures about these general rules.
Yes, sure. The classification may serve also for that. You look at the low-dimensional classes which we know in details and have some conjectures which try to understand also the reason.
Now we only look in 4 dimension. It's difficult.
Other questions? So let's thank the speaker again. Thank